So in this chapter 14, we are covering elimination reactions of alkyl halides. We already covered substitution reactions of alkyl halides, and now we are looking at elimination reactions of alkyl halides. Now I know that you had a test earlier today, so you didn't have time to look at this material, and I will be covering it in maybe a little bit more detail then, as opposed to other chapters where you had time to examine it before and you were supposed to see the videos and read it before. So in an elimination reaction, as name indicates, groups are eliminated. There are different types of elimination reactions. In this case, we are going to examine only polar elimination reactions. And in such reactions, polar groups are eliminated. And you may recall from earlier chapters, polar groups are actually an electrophile and a nucleophile. So in this case, an electrophile and a nucleophile are eliminated from the neighboring carbons to give an alkene, or in general a pi bond. Typically alkene is the product, but in more general terms pi bond is the product, which means alkyne, triple bond, could also be a product. We will, in this chapter, limit our study to elimination reactions of alkyl halides. So in alkyl halides, then nucleophile that is being eliminated is halogen. And that halogen could be X halogen. That means fluorine, bromine, or iodine. So keep in mind that fluorine in this case is a leaving group. Previously, when we covered substitution reactions of alkyl halides, fluorine was not a leaving group. So substitution reactions did not work on alkyl fluorides. Elimination reactions work. So alkyl fluorides undergo elimination reactions. That means all of the alkyl halides undergo elimination reactions. So that's the nucleophile, halogen. Electrophile is proton. The most common electrophile in organic chemistry is proton, and so in this case, that's the electrophile. There are three mechanisms for elimination reactions, and they all involve the same processes. Removal of proton from beta carbon by a base. You will see in a minute what is beta carbon. Formation of carbon-carbon pi bond, and breaking of carbon leaving group bond. So all three mechanisms involve these same processes. The only difference is in timing. Mechanisms are E1, or unimolecular elimination, E2, bimolecular elimination, and E1CB, conjugate base unimolecular elimination. So this lowercase c means that CB is one term. So we read that first, conjugate base, unimolecular elimination. So as usual, we read it backwards, but CB is one term, so we read it first. And so here are the three mechanisms. E1 elimination is unimolecular elimination. And just like SN1 reaction, initial step was breaking of carbon leaving group bond. So carbon leaving group bond is broken to give it intermediate carbocation. And then carbocation loses neighboring proton to give alkene or pi bond. In an E2 elimination, we have concerted process, no intermediates, only transition state. So all of the bonds are broken and formed at the same time, which means base forms bond to hydrogen, hydrogen-carbon bond is broken, carbon-carbon pi bond is formed, and carbon leaving group bond is broken. All that occurs at the same time, and in the transition state, all these bonds are partially formed or partially broken. And then product. And finally, E1CB, which does not have corresponding mechanism. E1, of course, corresponds to SN1, E2 to SN2, but E1CB is kind of unique for eliminations. That's the case where this proton is acidic and could be removed by a base as acidic proton. So removal of that proton gives conjugate base, or carbanion. That's why it's conjugate base unimolecular. Gives this carbanion, and then free electron pair displaces the leaving group in the second step. So again, two-step process, but unlike E1, where leaving group left first, now proton leaves first to give carbanion, and then Now, why is this called beta elimination? Actually, there are different types of eliminations, like alpha elimination, gamma, delta. Beta elimination means that proton that is removed is proton from beta carbon. This is old nomenclature that we still sometimes use. According to this old nomenclature, alpha carbon is carbon that carries the functional group. So in alkyl halides, carbon attached to halogen, fluorine, chlorine, bromine, iodine, is alpha carbon. Any carbon next to alpha carbon, attached to alpha carbon, is beta carbon. We could have, of course, up to 3 beta carbons. Sometimes we may have only 1 beta carbon. And then any carbon attached to beta carbon is gamma, any attached to gamma is delta, and so on. So we follow letters of Greek alphabet. This is sometimes even used in naming. Of course, you don't need to use it in naming. If chain is long, then you don't need to know the entire Greek alphabet and figure out what is the 16th, 17th letter of Greek alphabet. Instead, when chain is long, we simply say that last carbon in the chain is omega. And the second to last is omega minus 1, and then next to it omega minus 2, and so on. So that makes it a little bit easier. So you need to know alpha, beta, gamma, delta, and then at the other end we name it omega, omega minus 1, omega minus 2, and so on. So it's relatively easy. So beta elimination, by definition, elimination always occurs on alpha carbon. It removes nucleophile from alpha carbon. And question is, where is electrophile removed from? So if it's removed from beta carbon, then we obtain double bond. If it's gamma elimination, that would mean alpha gamma. That would form 3-membered ring. Delta elimination would form 4-membered ring, and so on. Alpha elimination removes hydrogen and bromine from the same carbon, and we end up with species called carbene. You may recall carbene from first chapter. You don't need to worry about any elimination other than beta elimination, one that forms pi bond. But just to let you know, there are other forms of elimination. And so now we are going to examine individual mechanisms. The best way is, if you learned SN1 and SN2 mechanisms, if you know them very well, then try to compare and contrast them. So first we are covering E2 mechanism. You will see that E2 mechanism corresponds to SN2, but there are differences. And in fact, there are important differences. So consider what is the same and what is different. What is the same is, of course, expression for rate, because it's bimolecular elimination, so bimolecular reaction. In bimolecular reaction, reaction rate depends on concentration of two species, substrate and reagent. So in an elimination reaction like this, bromoethane with hydroxide, like sodium hydroxide, to give ethene, and byproducts water and bromide anion. Reaction rate depends on the rate constant and concentration of substrate and base. Reagent is base in this case. Or, in specific terms, rate constant and concentration, in this case of bromoethane and hydroxide anion. Again, you need to know this expression, but there will be no calculations involving this expression. As I already mentioned, the mechanism, reaction is concerted reaction, which means all the bonds are broken and formed at the same time. That's what concerted means. So we have starting material, no intermediates, only top of the energy diagram, which is transition state, and then downhill to give products. And so in the transition state, bonds are partially broken and partially formed. In this case, in this transition state, hydrogen forms temporarily 2 bonds, so more than it can ordinarily form. Carbon, these 2 carbons form 5 bonds. But as I said, that's transition state. And note that reaction is endothermic, which means that enthalpy is not favorable. Product or products in general are less stable than starting materials. But entropy is favorable, reaction entropy, because we have more particles after the reaction than before. That means a degree of disorder is greater. So in this case, it's entropy that will make overall process favorable, and we may have to manipulate reaction conditions to make sure that that happens. There is another important feature of this reaction, and that's that base reagent attacks hydrogen on beta carbon next to carbon that is attached to leaving group. So degree of substitution is actually not very important because electron pair is related to hydrogen on the neighboring carbon. It's not nucleophilic addition. It's on hydrogen attack on hydrogen on the neighboring carbon. So degree of substitution does not matter. Typical bases that we are using in these reactions are hydroxide bases, like sodium hydroxide, potassium, lithium hydroxide, or various alkoxides. They also work really well. Those would be methoxide, ethoxide, and particularly T-butoxide, tertiary butoxide. Tertiary butoxide is very good because it's very strong base. We covered that in chapter 12. It's very strong base, but it's not nucleophilic. So there is no competition with substitution reaction. Because as you look at these reaction conditions, they are very similar to SN2 reaction conditions. And the question is, how do you know that you have elimination and not substitution? And sometimes actually you could have a mixture. We will cover that in a minute, or actually maybe not today, maybe next day, competition, substitution versus elimination. Nonetheless, to avoid substitution, we can use non-nucleophilic base, hindered base. And one of the best is butoxide. Potassium tertiary butoxide is commercially available, so that one is most commonly used. I don't know why it's potassium tertiary butoxide. Must have something to do probably with solubility or ease of preparation, because sodium tertiary butoxide should work just as well. But potassium tertiary butoxide is typically used. Alternatively, we can use methoxide or ethoxide or even hydroxide. Note convention. You see, in first two cases, only one alkene could be formed. But in third reaction, elimination of 2-chlorobutane with methoxide, first there is possibility for formation of two regioisomers, 1-butene and 2-butene. So those are two possible products. And then, in addition, 2-butene could be cis or trans. So we can draw two formulas, cis and trans, cis plus trans, or we can use these wavy lines. So you need to know this convention, what wavy line means. Wavy line means that either we have a mixture, as in this case. So in this case, it means we have a mixture of cis and trans. And so wavy line indicates that these bonds could be either down or up. That in some molecules they are down, in some they are up, and so that some molecules are cis and some are trans. We also use this notation when we don't know whether the compound is cis or trans. We may have only one, there is a reaction, and only one stereoisomer of 2-butene is formed, but we don't know which one. So we don't want to guess, and so we will use wavy lines. That's a little bit unfortunate that same convention is used both when we don't know stereochemistry and when we know that we have a mixture. But that's the convention. And from the context, you usually know what is the case, whether we don't know or whether we have a mixture. So in this case, we have three possible isomers. In elimination of 3-bromohexane, 4 possible isomers could form. 2 regioisomers, 2 and 3 hexenes, and each of them could be cis or trans isomer. And by the way, this wavy line is also commonly used to designate chirality center if we have a mixture of enantiomers, or if we don't know whether this is R or S. Let me see if there are any questions, and then we'll get to examination of degree of substitution. No. Degree of substitution and how degree of substitution in this case affects the outcome of E2 elimination. So in E2 elimination, we have to consider transition state. There is charge separation in the transition state. So if you consider here tertiary, secondary, and primary substrates, so tertiary alkyl halide, See, so carbon bromine, and this carbon is tertiary. This is secondary, and this is primary. Now there is charge separation, and it's very easy to figure out how charge separation works. You start with the base. Base was negatively charged, in this case methoxide. So oxygen had 1 minus charge. Once it begins to donate its electron pair to form bond with hydrogen, eventually that's going to be OH bond, and neither will be charged. But in the process of donation, charge on oxygen goes from -1 to between 0 and 1 to partial charge. So that's what we indicate with delta minus. And of course, charges have to alternate. We cannot have two identical charges, even partial charges, next to each other. There are some unusual mechanisms that occasionally where that happens, but it's highly unusual. And you should assume that what I'm telling you holds at all times. Maybe in advanced organic chemistry courses, if you take it, that's something that would be covered. So that means if charges alternate, if this oxygen in transition state is developing partial negative charge, then next atom in the chain, hydrogen, will develop partial positive charge, partial negative, is carbon. That will be future carbon of the double bond, partial negative, partial positive, and bromine that will leave as Br minus. When it leaves, it will have complete negative charge, full negative charge. Now, as bond is beginning to be broken, it's developing partial negative charge. So when you are comparing these three transition states, you can see that difference is on this carbon that is attached to the leaving group. It's developing a partial positive charge. So this carbon actually resembles carbocation. Even though it is not carbocation, because it's developing partial positive charge, it resembles carbocation, and it could be stabilized through hyperconjugation, just like any carbocation. Which means that the more substituted it is, the more stable it will be, because its electron deficiency that it is developing is going to be compensated by donation from the substituents, from CH bonds of the substituents. And that means that transition state that involves tertiary carbon is going to be the lowest energy, the most stable. And so that reaction is going to be the fastest. Then secondary and least stable transition state, highest energy, is going to be primary. That's going to be the slowest reaction. So in this case, the order of reactivity is tertiary, secondary, primary. So opposite from SN2 reactions. So remember that, very important, that order of reactivity is tertiary, secondary, primary. And that's because, in this case, electronic effects are important. It's the electronic effects that govern the reaction rate. Stability of the transition state, so stability of this carbon that is developing partial positive charge. In case of SN2 reactions, it was steric effects that were important. In organic chemistry, in general, effects that affect reaction rate and reaction outcome are either electronic or steric. And so you consider which ones operate and then consider them accordingly. And so even though E2 and SN2 correspond to each other, they are both bimolecular reactions. In case of E2 reaction, outcome is governed by electronic effects, and SN2 steric effects. And that's why the order of reactivity is completely different. So a very important point to remember. And then, of course, E2 eliminations could be regioselective, because we could have possibility for formation of different alkenes. Regioselectivity is indicated as Zaitsev versus Hofmann elimination. There is interesting historical note about Zaitsev elimination. Zaitsev was a Russian chemist. He was a mediocre chemist, never really accomplished anything in his life. Not that I want to kind of demean him, but that's truth. It was his supervisor, PhD supervisor, Butlerov, who discovered this effect. But he actually gave this work to Zaitsev so that Zaitsev could get a job. And also, he wanted to get back at Markovnikov, who opposed hiring Zaitsev on the grounds that Zaitsev wasn't good enough. Markovnikov was correct, but That's why it's called Zaitsev rule, even though chemist Butlerov was the one, a famous chemist, famous 19th century Russian chemist, who actually discovered this effect. And so this is what Zaitsev regioselectivity states, that hydrogen is removed from the beta carbon atom that is bonded to the fewest hydrogens. We can see how it corresponds to Markovnikov rule, and also you can get some idea what was Butlerov thinking when he gave this work to Zaitsev to get back at Markovnikov. So you can see here we have carbon-bromine bond, and there are two neighboring beta carbons. So hydrogen is removed from beta carbon that is bonded to fewest hydrogens. This is CH3 and this is CH2. I'm running a little bit out of patience with my cats. They just decide to go nuts right now. Okay. She is a little bit old, and usually she sleeps all day. But once each day she gets up and runs around the house like crazy. And that's the time now. I'm sorry. And that, of course, sets off other cats who give her a chase. Okay, so let me go back. So we have carbon-bromine bond, that's alpha carbon. And then there is CH2 group as a beta carbon and CH3 group as beta carbon. So hydrogen is preferentially eliminated from carbon that is bonded to fewest hydrogens. That's CH2. So 2-butene is preferentially going to be formed. 1-butene will be minor product. The reason behind it is that simply more stable double bond forms. Because stability of double bond is just like stability of carbocation. It is governed by hyperconjugation, by electron donation excuse me, from substituents. So this double bond, 2-butene, has two substituents. So two substituents that can donate electron density. One double bond, 1-butene, has one substituent. So more stable, more stable. And that's because in the transition state, double bond that is developing, that has more substituents, leads to lower energy transition state. Double bond with fewer substituents means higher energy transition state. And you can see that here. Reaction is endothermic. Another way to look into it is that transition state, according to Hammond postulate, resembles product because it's endothermic reaction. And so more substitute double bond is more stable than less substitute. That means transition state that leads to formation of more substitute double bond is lower energy compared to one that leads to less substitute double bond. That means that this product, what we would call Zaitsev product, is both thermodynamically favored because it forms faster, and it's also kinetically favored because it's more stable. Oh, sorry, it's kinetically stable. Kinetically, my cats are confusing me. I really don't want to get up and chase them away, lock them in a room, but I may have to. So this product, more substitute product, is both kinetically favored because transition state that leads to its formation is lower energy transition state. That means that reaction is faster, so it's kinetically favored. And it's also thermodynamically favored because it's more stable product. It's thermodynamic sink in this reaction. But while reaction is both, while the same product is both kinetically and thermodynamically favored, and consideration of either kinetics or thermodynamics will give you the same result, same prediction, this reaction is kinetically controlled. So the product that forms faster is the one that is the major product. Eliminations are kinetically controlled. Alternative mode of elimination is Hofmann elimination. And while most of the elimination reactions proceed through Zaitsev, Hofmann elimination is an exception. You need to know it, and you should be able to recognize it when you see it. So there are three factors that favor Hofmann elimination. First one is poor leaving group, fluorine. So if you see fluorine, elimination is Hofmann. That's it. Nothing to consider. Second factor is split into two factors, but basically it's steric hindrance. So if there is steric hindrance in a base, if you have sterically hindered base, that's going to be Hofmann elimination, or if you have sterically hindered substrate, Hofmann elimination. And of course, if both are sterically hindered, then Hofmann elimination is favored to a greater degree. So why? Now, Hofmann elimination, of course, is opposite of Zaitsev. So while in Zaitsev elimination, product was more substitute double bond, more stable, more substitute double bond. In the course of Hofmann elimination, product is less stable, less substitute double bond. So why poor leaving group leads to Hofmann elimination? So we should consider fluorine, which is a leaving group, so it could undergo elimination. But why fluorine favors Hofmann elimination? Well, consider transition states again. So this is elimination from 2-fluorobutane. This transition state would result in formation of 2-butene, so Zaitsev elimination. And this one, 1-butene, Hofmann elimination. So why is this one favored? Again, we have to consider electronic effects just as before. So as oxygen donates free electron pair, it ends up with partial negative charge, and that causes hydrogen to develop partial positive charge. Now this is important carbon. Previously, it wasn't important. When we were considering tertiary, secondary, primary, it was the other carbon that was important. When we are considering tertiary, secondary, primary substrates, is of elimination. But now it's the other carbon of the future double bond that is important. It's developing negative charge. And then this other carbon that is attached to leaving group is developing positive charge, and leaving group negative charge. But here is the problem. Leaving group is poor leaving group. By definition, poor leaving group won't leave. So what is going on is oxygen is donating electron pair. Effectively, it's pushing electron density on this whole system, on these 4 atoms. But fluorine won't leave. It's developing partial negative charge, but it won't leave. And so negative charge backs up, and it backs up in the middle. It backs up on this carbon. And so in the transition state, we end up with temporary backup of negative charge on this carbon before eventually oxygen is able to push everything through and leaving group leaves. And so these are the two possibilities, where negative charge could be on carbon that is more substituted or less substituted, because that results in more substitute double bond or less. With a negative charge, this carbon resembles carbanion. And as you would expect, stability of carbanion is opposite from that of carbocation, because with carbocation, we have electron deficiency on the carbon. And so the more substituents there are, they are donating electron density, they are stabilizing that carbocation because they are compensating its electron deficiency. But opposite is the case in carbanion. In carbanion, you have carbon that is unstable because it has excess electron density. It has free electron pair. And now, if you have more substituents that are donating even more electron density to it, they are making it even less stable because they're pushing even more electron density on species that is already unstable because of the excess of electron density. For that reason, the order of stability of carbanions is opposite from that of carbocations. So the less substitute carbanion, the more stable it is. So the least stable carbanion is tertiary, then secondary. More stable is primary, and more stable is methyl. In this case, of course, since double bond is forming, we can't have methyl, but primary is the one that will be the most stable. And so that's more stable. This resembles carbanion, so this is more stable, lower energy transition state. And so that's why Hofmann elimination works. But remember, Hofmann elimination works only if leaving group is fluorine or there is steric hindrance. So we just covered that poor leaving group. And you can see selectivity is not great, but it's noticeable because odds of 2 double bonds forming is 50-50. So 70-30 is big difference from 50-50. But still, it's not selectivity that you would like 95-5 or 99-1. 70-30, that's, it's noticeable, but not that big. Now, in terms of steric hindrance, that effect is steric. Simply a base that is sterically hindered, or if substrate is sterically hindered, or if both are sterically hindered, then because of the hindrance, it's easier to remove proton from the edge of the molecule less substrate carbon because it's less sterically hindered than one that is more sterically hindered. And so when there is steric hindrance in substrate, basically substrate is tertiary, or steric hindrance in base. And the only one that you know that is sterically hindered is tertiary butoxide. Propoxide with two metal groups is somewhere in between. It's kind of sort of hindered. So I wouldn't give you something like that without previously teaching you about details and to consider that. So tertiary butoxide is the only base that you would consider. So if you see tertiary butoxide as a base, or tertiary substrate, or both tertiary, then Hofmann elimination predominates. And regiochemistry, that means Hofmann and Zaitsev, is always kinetically controlled. These reactions are kinetically controlled. So elimination reactions are kinetically controlled. And even if sometimes consideration of thermodynamic factors would give you correct answer, still reaction is kinetically controlled. Now, substrates that contain double bond or aromatic ring, you should ignore that. That's something discovered, I believe, in chapters 17 and 18. I don't know how my colleague Elijah St. Germain will be covering this course, what he will be doing, but this is for you at that time when you cover elimination reactions to go back and read this, and that will be studied at that time. So just kind of to remind, this is covered in one of those chapters, and also same mentioned here so that you can relate those materials. But it's not on the test now. You don't need to know that now. If you read it now, that's good, but you don't need to know it. So that's page 346. So this middle of the page 346. Substrates that contain a double bond or an aromatic ring, you don't need to know that. That's not part of course now. So that was E2 mechanism. Before I cover E1 mechanism, let me check if there are any questions. Okay, no questions. So, of course, the other mechanism that is important is E1 elimination mechanism, and that's unimolecular elimination. E1 corresponds to SN1. In an E1 elimination, reaction rate depends only on the concentration of substrate, and that's alkyl halide. So here we have an example of reaction of tertiary butyl bromide with water. Product is 2-methyl propene, and of course, aqueous solution of hydrogen bromide. Reaction rate depends only on the rate constant multiplied by concentration of substrate, or in this specific case, rate constant and concentration of alkyl halide, tertiary butyl bromide. Reaction mechanism involves two steps. First, slow step is breaking of carbon-leaving group bond, carbon-bromine bond, to give carbocation. So that's slow rate determining step. Second step is product determining step. In the second step, water acts as a base, picks up proton beta to carbocation. Carbocation is alpha carbon. There are 3 beta carbons. So from one of the beta carbons, water picks up a proton, and that results in formation of corresponding alkene. And now you know why second step is called product determining step. First step was rate determining step, second product determining step. Because in both SN1 and E1, first step is the same. When you see this first step, you don't know whether the reaction is going to be SN1 or E1, because intermediate carbocation is the same. It's only when the second step occurs, then you know whether substitution, SN1 reaction, or elimination, E1 reaction occurs. That's why this is called product determining step. In this step, in the second step, is determined what is the product going to be. And that's actually shown here. So first step, RDS, rate determining step. Second step, product determining step, or PDS. E1 elimination is always Zaitsev. So regioselectivity of an E1 elimination is always Zaitsev. The only time Hofmann elimination occurs is if we have E2 mechanism. Of course, since E1 elimination proceeds through carbocation, then rearrangements are common. So whenever possible, secondary carbocation will rearrange it to tertiary. And then elimination of proton will occur from a tertiary carbocation to give the most substitute alkene, the most stable, the most substitute alkene. Don't worry about the second one. That's if you already have double bond present. That's again something that would be chapter 17 and 18. And that's not something that you need to worry about now. It's again here to relate that to the material, the future material, because at that time, when you study those reactions in those chapters, I forgot, I believe it's chapter 17. Then you should return and review these chapters 12 and 14. So, but first rearrangement is something you definitely need to know. That if secondary carbocation forms, whenever possible, it will rearrange to tertiary, and then tertiary eliminates in such a way to give the most substitute double bond. Of course, other eliminations would give less substitute double bond. And then we have very important aspect of elimination reactions, and that's stereochemistry. So far, we were looking at regiochemistry. So whether double bond is more or less substituted. Stereochemistry means that double bond could be cis or trans. So which double bond forms, cis or trans? We have to consider E1 and E2 eliminations separately. So in E2 eliminations, we consider, like this, elimination from 2-bromopentane in ethoxide. We consider transition state. So these are Newman projections, of course, of the transition state. You can see in this particular experiment, we have two regioisomers, 2-pentene and 1-pentene. And you can see that Zaitsev rule is followed, more substitute double bond is obtained. 2-pentene is the major product, but only 41%. 14% is, 41 and 14, total of 55% of Zaitsev product is formed. Remaining 45% is 1-pentene and various substitution products. So various substitution products, that means 2 enantiomers of substitution product. So here we have trans product formed. So this is only Zaitsev product shown, only the most important Zaitsev product, 2-pentene. But it could be trans or cis. And you can see trans is predominant. So why? Well, for the elimination to occur, we have elimination. In the course of elimination, we have breaking of carbon-bromine bond and carbon-hydrogen. So in the transition state, these two bonds have to be in the same plane. That's because when those two bonds break, they will form a pi bond. And of course, pi bond is in particular plane. So these two bonds already have to align themselves in such a way to be planar, in the same plane. And the most stable conformation is anti-periplanar, when two bonds are anti to each other. That means on the opposite sides. Alternative arrangement is when they are syn-periplanar. When they are, so anti would be opposite from each other. Syn would be on the same side. You will see that as the last example. But that's eclipsing conformation. Syn-periplanar is eclipsing conformation. Remember that from chapter 4. So you can see how organic chemistry is related to what you learned before. So what we do is we make a model. And here is model shown Newman projection. So this is closer carbon. This is carbon 2. So when you look from the right, you can see bromine pointing up. It's bromine pointing up. This metal group down to the right. Hydrogen is not shown, down to the left. And this is back carbon, CH2 group with ethyl group. So this is, and we can rotate that back carbon. So in this first transition state, you can see that methyl and ethyl group are gauche to each other. Gauche conformation exhibits steric hindrance. Eliminations is there on the same side. See, when hydrogen and bromine are gone, pi bond forms here, and methyl and ethyl end on the same side, right here. That's cis, they're on the same side. if they're on the same side in transition state, they will be on the same side of double bond in the product. That's cis steric hindrance. That's unstable transition state because of the steric hindrance. Second transition state, when we rotate 120 degrees back carbon, now methyl and ethyl group are anti to each other, as far apart from each other as possible. They're on the opposite sides. So when hydrogen and bromine are gone, double bond forms, and they will be on the opposite sides of double bond. That's trans. So that's more stable, lower energy transition state, and that's favored transition state for formation of the product. So this transition state is the lowest energy and it gives trans product. Another 120 degrees rotation gives transition state 3. But in that transition state, carbon-bromine and carbon-carbon bond are aligned, are antiplanar to each other. And we cannot have elimination there because carbon-carbon bond would have to break. Base cannot remove carbon. So this transition state 3 cannot lead to an elimination. Finally, there is possibility for this transition state 4, eclipsing. So obviously I have to cheat a little bit. This hydrogen should be right behind bromine and this behind hydrogen. Methyl and ethyl are eclipsing. Obviously in eclipsing conformation, in addition to steric strain, we have high degree of torsional strain. So that's very unstable conformation, transition state. And in general, this is not reasonable transition state. But in some small rings, some small cyclic compounds, that's the only way how elimination can occur. So this is reasonable if this methyl and ethyl form a ring, if they are connected to form a ring, because then you can't have rotation. And so that's only reasonable if it's a ring. But it's still reasonable. So you need to know for each of these 4 transition states, you need to know their features, what they lead to. This one leads to less stable product, so minor product. Second, most stable product, major product. Third, cannot lead to elimination. Fourth, can lead to elimination, but only in rare cases, typically cyclic compounds. One thing, if you didn't notice, is that there are 4 possible cases, 4 possible choices that we can consider as candidates for transition states. And if you think about the exam, on an exam on multiple choice, you have 4 choices, A, B, C, D. That's quite a coincidence, right? So keep that in mind, that you really need to know each of these 4, because depending on the question, each of those 4 could be correct answer. So that's stereochemistry of E2 eliminations. Stereochemistry of E1 eliminations is related to it, but it's a little bit simpler because the intermediate is carbocation. So we consider elimination from carbocation. So this closer carbon is carbocation. It's not carbon-bromine bond. Bromine is already gone. So it's sp2 hybridized carbon, and this is empty orbital. Now, on the back carbon, carbon-hydrogen has to align with this empty orbital, so that when hydrogen is gone, when base picks up a hydrogen, electron pair will flow into this orbital and form a pi bond. So again, we have transition states. Now we have 3. So in this case, for multiple choice exam, if this is a multiple choice exam, I will have to somehow come up with 4th one. And so you should recognize that it's not one of these 3 and clearly not reasonable. So if 2 substituents are on the same side, obviously there is steric hindrance, and they will be on the same side in the product, which means, again, because of the steric hindrance, this product is disfavored. It's less stable intermediate, and so it ends up being minor product. So in this case, I rotated closer carbon. So I moved this methyl group, so 180-degree rotation of the closer carbon. So now that rotation results in 2 substituents being on the opposite sides. Upon removal of the proton, pi bond forms. If they were on the opposite sides of carbocation, now they're on the opposite sides of double bond, so that's trans. So now trans product is again favored. So as you can see, E1 and E2 eliminations both favor trans products, but for different reasons. In E2 eliminations, it's stability of transition state. Lowest energy transition state gives the major product trans. Here, lower energy carbocation gives trans product. And finally, third possibility is that carbon-carbon bond is aligned with empty orbital. That cannot result in elimination. Again, you need to know not only which one leads to cis and trans, but which one cannot result in a reaction. Because any one of those could be a question. And here's a summary that each of them could result in, that each of them results in major formation of trans product, but for different reasons. And again, here, summary, we have 4 different candidates. So cis, trans, no reaction, reaction only in very rare cases. And in this case, case 4, we don't have choice cis trans, because that's usually for some reason rotation is not possible, and then whatever it is the case, whatever arrangement is, then elimination occurs. But as I said, that's rare. So you need to know for that last one that it occurs only in rare cases. Maybe on the test, if you have it, CH3 and CH2, CH3 methyl and ethyl will be connected in a ring. So you would have like CH2 here connecting the 2 or something like that, if that shows up on the test. Let me see. Yeah, and then final very important thing is regiochemistry of elimination in cyclic compounds. So that's very important. That's very often on the exam. So in cyclic compounds, because rotation is prevented, still cyclic compounds would tend to avoid this 4th case because it's really high energy transition state. And so sometimes elimination goes in unexpected way, kind of the wrong way, and you end up with Hofmann elimination or unexpected elimination, even when you would expect something else. So in this case, we have trans compound, that is E2 elimination. So trans 1-bromo-2-methyl cyclohexane, and elimination with potassium tertiary butoxide. And so what's the product, or the products? In this case, if you were asked for all the products, you would probably expect more substitute alkene to be major and less substitute alkene minor. Or if you recognize this as hindered base, okay, then it's Hofmann elimination, then this should be major, this should be minor. But either way, you would expect 2 products, whichever way you do the analysis. Instead, we get only Hofmann product. That's not Hofmann elimination if you get 100 to 0. It's Hofmann is if you get 70-30, 80-20, and same Zaitsev, 70-30, 80-20, 85-15. But 100 to 0, that's something else. So something else is operating when it's that highly regioselective. And that happens, in this case, only in cyclic compounds. And basically what it means is that elimination to give more stable double bond is somehow prevented. And the elimination can occur only one way, by default. And so here is what happens. When you consider trans 1-bromo-2-methyl cyclohexane, a lowest energy chair conformation, again chapter 4, you can see this carbon-bromine bond should be aligned properly for elimination. And actually this is this case 3. If you look at, see, it's the case 3, where carbon-bromine and carbon-carbon bonds are aligned. Elimination cannot occur. It's for you to be able to visualize it, I put that bonds in bold. See, these are the bonds that are antiperiplanar to each other. Carbon-bromine and carbon-carbon. And here, the other way, also carbon-carbon. So actually, elimination cannot occur from the lowest energy conformation. So 6-membered ring has to flip into higher energy conformation, from di-equatorial into diaxial. And in fact, that's always the case with 6-membered rings. The groups that are eliminating are axial. They have to be axial. That's the only way they are oriented properly. Otherwise, ring would be broken in the course of elimination. But now, when you look at axial bonds, of course, carbon-bromine has to be axial. Carbon-bromine is carbon 1. This carbon that is attached to methyl group, that's carbon 2. And you can see bond that is antiperiplanar. It is axial, is carbon-carbon. And we just discovered that, or discussed it numerous times, that bond cannot break. It's carbon-hydrogen that can break. So only one bond can break. and that's the only bond that can break, and that's the only product that is formed. And so now, as bromine is gone, numbering is different. It's 1, 2, 3. It's 3-methyl cyclohexene. So from this, you can draw a conclusion that bonds that are eliminating in 6-membered ring have to be axial, diaxial, and they have to be trans to each other. So even without doing this entire analysis, simply when you look at the starting material, two groups, bromine and hydrogen, have to be trans to each other. So you look at this bromine, it's up. Hydrogen that is eliminating from the neighboring carbon has to be trans, down. So you look at this carbon, methyl group is down, hydrogen is up, cannot eliminate, because with up bromine, hydrogen has to be down to eliminate. Only this carbon has down hydrogen, that's the one that is going to eliminate. If bromine were down, then this hydrogen could eliminate, and this would have been the major product. But with up, down bromine, down hydrogen has to eliminate. So that's another way to look at it without having to go through this whole analysis. Two groups that are eliminating have to be trans to each other. And that's shown here. See, we have bromine. Elimination of bromine can now go only this way, down, away from these two methyl groups. When you have two methyl groups, then elimination cannot go this way to this carbon, because there are no hydrogens available for elimination. On this carbon, we have placed two isotopes of hydrogen, protium H and deuterium D. And exam question could be, which one is going to eliminate? Trans to bromine. So if bromine is up, down is going to eliminate deuterium. So product will have 100% protium, because trans eliminates, so deuterium is gone, protium is left, product will have 100% protium, 0% deuterium. If bromine were down, only protium would have eliminated, and you would have 100% deuterium in the product. So very important analysis, and as I said, it comes up on exam very often. E1 eliminations are much simpler in cyclic compound. E1 elimination in a cyclic compound proceeds in such a way that most substituted double bond is formed. That double bond is always in the ring, because double bond that is outside the ring, we call that exocyclic double bond. Inside the ring, endocyclic. Exocyclic double bond is very unstable. This is a very unstable compound. In organic 2, you will learn how to make these. They are actually really difficult to make. We have a reaction called Wittig reaction that makes them in very good use. But bonds inside the ring are generally preferred, and among those bonds, the most substituted double bond is the one that forms preferentially. So in this case, you see loss of bromine, gives carbocation, tertiary carbocation, and then this tertiary carbocation can eliminate to give 3 possible alkenes towards this methyl group CH3 to give exocyclic double bond. That's least stable, that doesn't form in very large amount, trace amount, typically 1% or less. It can go towards CH2 group. That would be Hoffman product, less stable double bond, less substitute, that's minor product, and the most stable is tetrasubstitute double bond. So if mechanism is E1, then the most substitute, the most stable double bond forms. Okay. And that's what I planned to cover for today. Now, I mentioned several times E1 versus E2 mechanism, and if this is the mechanism, that's the outcome, and so on. And I never mentioned how are you going to figure out whether mechanism is E1 or E2. Also, I told you that number of times we have competition between substitution and elimination. And again, how do you know whether reaction is substitution or elimination? That's something that we'll cover in our final lecture. So next day, in the second part, that's what we are going to cover and summarize this chapter.